Alright, let's talk about asymptotic notation. So you've probably seen this before in data structures. If you haven't, that's alright. We'll basically start from the ground up on it. But the idea here is that when we're talking about running time or memory usage, sometimes we want to talk about it in terms of sort of asymptotic characteristics and get rid of some of the lower, smaller details that aren't as important all the time. So for this set of slides, we're going to be looking at total running time. We'll talk about asymptotic running time, and we'll talk about asymptotic notation. There is an exercise that goes with this set of slides, and it'd be great to have that out and sort of follow along and try to do that before we talk about them on the slides themselves. Alright, so if you're looking for extra resources on asymptotic notation, I'll have a link on the course website. You could also look at Chapter 3 of the Corman book, the Introduction to Algorithms. It's a really thick textbook. It'll pretty much have content for everything we talk about in this class. Alright, so when we're trying to compare algorithms and data structures, this is something we do all the time. We like to compare them based on speed and memory usage. There are a few other things you might want to compare them based on, but maybe code complexity or any sort of extra metrics like that. But for the most part, we care about comparing them based on speed and memory usage. But when we do these comparisons, we don't always care about little details. So on assignment 1, you'll see that you're going to compare merge sort and insertion sort, and under some circumstances the differences between the two are really small, and sometimes the differences between the two are really large, and we don't really care about the minute details, like is it a fraction of a second faster or is it 10 times faster. So that would be like comparing a n-squared algorithm compared to an n algorithm. And then those are sort of, that's what we'll be talking about in this set of slides, is when do we not care about the little details. And in this set of slides, we will ignore details like data locality and differences among operations. So I mentioned before that, for example, division and multiplication usually take longer than addition and subtraction. Those are the things that we're going to ignore when we're talking about asymptotic notation. Something that it's hard to ignore is data locality. That's something we'll talk about later in the semester. But that tends to make, sometimes, depending on how much data you're operating on, as big of a difference as asymptotic complexity does. Alright, so what am I talking about when I'm talking about little details? Well, let's say we have an algorithm and it's a loop, and we have a coefficient out in front that's 0.01, so that's however many operations we're doing in the loop, that's the coefficient for the running time of those operations. So let's say we have a piece of, we have an array, and we're looping through all n elements in the array, so all items in the array, and for each one we're doing sort of that amount of work. That 0.01 amount of work per element seems really low, but when you compare it to doing some other operation on the n elements. Oh, I didn't fix these slides yet. This should really be n squared again. I had this problem in the last set of slides, and I still haven't fixed it here. So let's say we're doing 100 unit of work, but we're not doing it for all n squared possible times we could be doing it. So this would be like having a nested for loop. So we go over the elements once, and then for each time we go over the elements, we go over all the elements again. And we're doing very little work for each of those. Here we're doing a lot of work, but we're not doing it in a nested for loop kind of code. So even though this is a lot of work each time we're doing something compared to here we're only doing it n log n times, and here we're doing it n squared. And the n squared ends up costing a lot more time as you end up with really large values of n. So we say here, asymptotically, our blue line here is much better than our orange line. That's what we mean about asymptotically. So let me give you a little bit more concrete example where we're looking at code. So take a look at this code and just add up the total number of operations. So I'm saying that function 1 here has a total running time that we computed by examining the code and computing it like we did for merge sort, and function 2 has a total running time of this. So what's the total running time of running function A and then running function B? So I'll try to pause in the lecture slides and give you a chance to pause the video. So hopefully you've paused and you've come up with something that's kind of like this. So we have 2n log n plus 2n minus 50 plus 1 plus 3n log n plus 6n plus 48 plus 1. So where did I get all those from? I just took this, added it down there, that, put it down there, except for the plus 1. The 2 plus 1s come from the fact that we're doing some assignments here. So that's our total running time, and we can simplify it to the total running time of running those two functions and assigning the output to variables a and b is 5n log n plus 8n minus 200. So when we want to look at the running time of running those two functions, a lot of times we don't care about small details. So we don't care that there's maybe a loop in there and we're doing 8 units of computation for each item in the array or whatever this function's actually doing. In fact, we might not care about the n part here either, because maybe the amount of work that contributes is really insignificant compared to the 5n log n. And likewise, it's easy to get rid of constants or negative constants, even and more so, because we can just say, okay, well, if this is t of n is exactly equal to that, well, we can just say t of n. We know that it's greater than or equal to something that's less than this. So that would work. So we're just getting rid of some of the little extra details that we don't need. And why do we do that? We want to be able to quickly glance at the running time of an algorithm and be able to compare it to other algorithms. So instead of saying that the total running time is this, we're going to say that the total running time is big O of n log n. And it's really easy to see, okay, well, how does this compare to other algorithms we know? N log n, okay, so maybe that's some sort of binary tree, binary recursion tree type of function that we're looking at. All right, well, what exactly does it mean when I have some function here that you're used to seeing things like logarithms and constants and n, your variable here? This would just be like a plot where we've got n versus some vertical axis. Well, what does this mean? Well, instead of saying equals, we don't really say equals when we're talking about asymptotic complexity. We say belongs to, or another way to say it is, so 5n log n plus 8n minus 200 is big O of n log n. So those are two ways of saying sort of what that equation is really meaning. Well, what does it mean to say that some function belongs to or is big O of some other function? Well, we can only say that if and only if we can find values for c and n naught that makes this equation hold. And an important part here is that c and n naught cannot depend on n. It's really easy when you're working on a homework assignment or a proof to accidentally say like c is equal to, I don't know, 2 to the n. That doesn't work because it has to be a constant. C here is a constant. And if it depends on the size of the input, well, that's not constant depending on the input. It's linear with respect to the input or exponential with respect to the input like I had here. All right, so to make this make more sense, why we have this equation and why that means we can get rid of leading coefficients and lower order terms, we're going to go through a bunch of examples in the next video.